So starting with this problem from SHM Pathfinder. So the problem is given as a small bar of mass m is affixed at one end of a light rod of length L, the other end of which is hinged to a fixed pivot on a wall. One end of a spring of force constant K is attached on the rod at a distance d from the hinge. The whole situation has been depicted in the figure itself from the hinge, and the other end of the spring is attached to the nail of the wall. From this one to this line, this has been given in the figure itself. Now the question comes: in equilibrium the rod stays horizontal. So at equilibrium, if the rod stays horizontal, you may write this one is mg, this is like you may say kx is the force on the spring, this is what kx sin theta naught, kx cos theta naught, and there is a reaction force, hinge force, which is balancing this kx cos theta naught rx. Okay, now what you need to do: if the ball is pulled slightly downwards and released, the system begins to oscillate. Find the time period of the small amplitude of oscillation. So what can I do? Let's I have given a small displacement to this mass m, and as you may see, whatever the color I am using right now is the violet color. Okay, so this one is a small displacement. So whenever the mass will get displaced, the spring will also displace. This is the initial condition, and this one is the later on condition, right? So if this is phi, you may write this one is what? This one is phi d. If this is phi d, so this is theta naught given, this is theta naught. So if this is theta naught, this one you may write also theta naught, because the difference in angle is very small. Okay, so what is happening there? Just drop a perpendicular, as there is many DC Pandey problem you might have done. So from the initial position you need to drop the perpendicular. As you need to drop the perpendicular, after dropping it you may write this one is theta naught, this is 90 minus theta naught, this one is theta naught. So if this is phi into d, because the distance given in the question is this one is d, so as this one is d, you may write L is equal to r theta equation. L is equal to r theta, L is L, r is how much d, and theta is phi, so L is equal to d phi. So this one is phi d sin theta naught, this length, this extended length. Okay, so the initial condition was like this. As it is in equilibrium, you may write mgl is equal to kx cos theta naught into d. What I have written here, kx sin theta naught into d. That is a wrong one. Kx sin theta naught into d. Okay, because sine force is acting upward. Mg trying to pull this downward, and kx sin theta naught is trying to pull this upward. So this is mgl is equal to kx sin theta naught d. Now what is happening? If you further pull it, what you are getting? You are getting an acceleration, right? An angular acceleration. Okay, so if we have pulled it like this way, now this is mg. I am assuming that this line is like perpendicular to this one, because the angle of deflection is very very small. So what I can write? I can write is mg L minus mgl. Basically I am writing minus mgl because it is trying to pull it downward, and in the anti-clockwise sense, and in the clockwise sense what is happening? kx sin theta will try to pull it upward, kx sin theta into d. So in place of x, what I need to write? I need to write the new x, that is x plus phi d sin theta. So what is happening? This mgl and kx sin theta naught d cancel out, so the remaining is k phi d sin theta naught into d sin theta naught, that is k phi d square sin theta naught square, that is equal to ml square alpha. I is moment of inertia and alpha is the angular acceleration. So from this equation alpha can be find out. Alpha is equal to kd square sin theta naught by ml square into phi. So you can find out omega, and onward you can find out time period. Thank you.